Hey guys, we are back for 7.2. We're going to see some new integrals and how to operate with them. So 7.2 is trig integrals. So it turns out 7.2 and 7.3 both focus on trig, but in very different ways. Okay, trig integrals. And so we've got the first, we're just going to dive straight in to our first example here, which asks us to integrate, obviously. Part A is the integral of sine to the fifth x times cosine squared x dx. Okay, so it turns out the integrals we're going to see are going to take this sort of basic shape that you see there. Here we have powers, a power of sine times a power of cosine. We're going to see some other combinations, secant and tangent and that sort of thing, and powers of them, and just how to work with, different details on, are the powers even or odd or whatever they might be. You're going to see a lot of U substitution here. And we're going to walk through just different techniques of different situations. Okay, so as we look at this one, one thing I just want to point out from the beginning is this power on the sine. So just kind of imagine this for a second. If this fifth power was not there, and it was just sine x times cosine squared dx, this would be a very straightforward U substitution, right? We could take U to be cosine x, du would be negative sine x, right, if the power wasn't there, and that would unfold pretty well. Same idea if the squared was not here in the cosine. If that was just cosine x, we could take U to be sine x, du would then be the cosine x dx, and it'd be actually one of the simpler, very simple as U substitutions go anyway. But now when there's a power on both of them, this is a whole new ballgame. But we're still going to end up using a U sub. Okay, so what are we going to do? I'm going to walk through this one, and then we're going to refer to, you might see that trig integral guide that I posted along with the lecture videos. It's a PDF. I'm just going to walk through this one, and then we're going to refer back to that. And then we're going to use the guide for future examples. Okay, but taking a look here, what are we going to do? And here's the idea. I'm going to separate one of the sine x's. Okay, so I'm going to break it off of that fifth power, dropping it to a fourth. This just gets repeated, and I'm going to multiply by sine x just off the end. All right. See if I can get a slightly better focus here. Okay. Then I'm going to say, okay, I'm setting this up because in a moment, we're going to do a U substitution. We're going to take U to be cosine x. And this is going to fit our du. We think, how can you take U to be cosine x? Well, we can't just yet. So focus on that remaining power of sine. We're going to use a well-known trig identity to rewrite this. It's one of those Pythagorean identities. Probably the most well-known trig identity of them all is sine squared x plus cosine squared x equals 1. Okay, so how is this going to work? Well, think of solving for sine squared x, right? Subtract the cosine squared over here. So 1 minus cosine squared x would equal sine squared. Of course, we have sine to the fourth, so we'll have to square that whole thing. And we'll get this. 1 minus cosine squared x, quantity squared, because the fourth power. And then we're just repeating the other parts. Okay. And now we're ready for our U substitution. Let's do it. I see a bunch of cosines and powers of cosine, and then I've got my sine x dx. So take U to be cosine x. Du, of course, is negative sine x dx. That negative's no big deal. We can just move that right over to the other side. Negative du equals sine x dx. This is the way I like to think of U substitutions, by the way. If there's a constant or a coefficient that you don't need or need to adjust, I like to think of just moving it to the other side. You may have learned U substitution slightly differently. Depending on the teacher, there's different styles. but it all gets to the same goal. I just find this the most straightforward and easiest to think through. Okay, so then I can see, all right, sine x dx is going to be negative du, and then the others, well, those cosines just become u, so we get this nice integral right here. Quantity 1 minus u squared squared times u squared times negative du, and maybe I'll just bring that back on the screen. So there's a u squared and a u squared and negative du. Okay. Now there's going to be a little bit of algebra to, to multiply this out, but certainly nothing we can't handle. So from there, maybe think I'll bring the negative all the way out to the front. Let's go ahead and FOIL our quantity that's being squared. 1 minus 2u squared plus u to the fourth. And now let's distribute our u squared. Multiplying it all out, we've got the negative integral u squared minus 2u to the fourth plus u to the sixth du. And we're almost there. Now, antiderivatives of each of these. Hopefully, and simple antiderivatives or, antiderivatives that were coming really quick to you back in Calc 1. They kind of knocked the cobwebs off a little bit because you used to be able to do these most likely very, very quickly without much thought at all. But now that it's been some time, you're like, how does that antiderivative work? Okay, so we've got 1/3 u to the third minus 2/5 u to the fifth plus 1/7 u to the seventh. There'll be a negative on all those, and don't forget your plus c. Of course, we need to go back and replace the u with cosine x. So we can get to our final answer right here, negative 1/3 cosine to the third x plus 2/5 cosine to the fifth x minus 1/7 cosine to the seventh x plus c. And there is your indefinite integral. Now, what's nice about indefinite integrals, you can always take the derivative of your answer, and it should get you back to where you started. So this one, I won't go through it, but yeah, there'd be a trig identity you would need to get it all the way back to the way it began, since we used a trig identity in the middle. Okay, I think we feel pretty good about this. Let's see another one. Oh, actually, at this point, let me refer back to that trig integral guide. If you haven't opened it up yet, check it out. So let me kind of bring it even back to the statement of the problem here, part A. So you see in that guide, we kind of have these two major categories of integrals that we're going to see, either powers of sine and cosine or powers of secant and tangent. And then there are methods for what exactly are the details and what those powers are doing. So what we just dealt with was the first one under the sine and cosine. So you think of n as being the power of sine and m being the power of cosine. Well, we had n odd, right? The power of the sine was odd, and so we knew we could use method number 1 there. Now it turns out that same approach could be used if m was odd or if both of those powers are odd. So only one of them needs to be odd or even both, and this method's going to work. And now we see, okay, what to do. So separate the odd power. When I say separate the odd power, I mean take the one that's odd and break one of them off, put it on the end. So if they're both odd, well, you've got a choice. If only one of them's odd, obviously pick that one. And then rewrite what's left after you separate that one power using that trig identity, sine squared x plus cosine squared x equals 1. So, of course, here it was the sine that we separated, so we're going to use the identity on the remaining sine. And what does that do for us? Puts everything else in terms of cosine, and then has that one sine off the end, allowing us to do a u substitution. Okay. Obviously, we're going to see more styles as we keep going, so let's go to part B. This is just a power of sine. So here we go. Part B is the integral of sine to the fourth of 6x dx. Sine to the fourth 6x dx. You think, okay, well, I only have sine here, and it's an even power. So that's going to be method number 2, where it says both n and m are even. And you think, wait a second, both m and n are even? Well, couldn't we say that the power of cosine is even here? You could think of it being to the power 0, if you want to get technical. Or you just think, well, the only thing that appears there is a sine and it's an even power, so that's good enough. Okay, what are we going to do in this case? So here we've got some other trig identities. These are double angle formulas for sine squared x and cosine squared x. So we'll use the sine squared x. We're going to rewrite, thinking of that as 1 minus cos 2x over 2. But of course, some of the details we've got to adjust, right? So we've got sine to the fourth. So, we'll need to put parentheses to square the whole thing. Also, our angle is 6x. And you see there in the formula, the angle x in the sine squared becomes 2x in the cosine. So the idea just being you need to double it. Okay, so using that identity, here is what we've got. We're going to rewrite sine to the fourth 6x as 1 minus cosine 12x all over 2. And all of that is being squared. Okay. And now what have we done cleverly? Well, we had a fourth power, and now, well, we've doubled the angle, but that's not a big deal to us as far as antiderivatives go. And now it's just going to be a square. Now we're going to have to multiply this out, obviously. But we turned a fourth power into a square. So we're making things simpler. Okay, let's see how it plays out. Since we just have a 2 in the bottom, let's go ahead and just apply the square to both numerator denominator separately, and I'll even pull out that constant. So we'll get a 1/4 coming out front. And I'm just going to leave this as 1 minus cosine 12x quantity squared for now. Of course, the next line is going to be to FOIL that. So let's go ahead and pause the video at any time if you need to, obviously, if you need to write these things down and I'm speaking a little bit too quickly. Okay, so we've got the 1/4 on the outside, integral 1 minus 2 cosine 12x plus cosine squared 12x. And you can see, okay, we've made some progress. Both of these first two terms, we can take the antiderivatives of them as they are, right? Certainly we can do it for 1, and even 2 cosine 12x, we'll be able to do that antiderivative since it's just a first power of cosine. But let's execute that a little bit later. For now, let's focus on this, cosine squared 12x. Okay, well, that on its own, we're not able to do an antiderivative. But hey, if you refer back to the trig integral guide, which situation does this fall into? Hey, that's an even power of cosine, right? So we started with the fourth power sine. Okay, we made it smaller. We're still in that, but it's getting better. Okay, so we're going to end up using the identity for cosine squared x here in a second. Maybe one step in between, though. I like to do this just to make things really clear for lecture purposes. You don't necessarily have to do this when you are doing problems on your own or on tests or anything. But for make this really clear, so I know I can do these, and I'm going to pause on that, not do them yet, but I'm going to just think of the integral here plus 1/4 and the integral here. Of course, that 1/4 needs to go to each. Okay. So this one I'm not working with yet. It's ready to go. Let me focus here. So a nifty trick, and maybe you guys have seen this before. If you put these little tally marks, little tick marks, that means, okay, just copy that. But I don't really want to copy all that for no, if I don't have to. Okay, then back over here, we're going to use that identity on the cosine squared. So now it's 1 plus cosine, again, double the angle, 24x all over 2. And now we've reduced that to a first power of cosine. And we are very close to getting the answer to this problem. Cleaning it up just a bit, I'm going to move that 2 out, make a 1/8 there. Again, copying what's the first half, that integral there. All right, now I think we're ready to execute some antiderivatives. And I know I'm definitely talking too fast now because there's a lot to write. Okay, so I'm leaving the 1/4. Antiderivative of 1, of course, is x. Antiderivative of 2 cosine 12x would be this. So you can think, you could use a u substitution here. Take u to be the 12x. However, this is, as far as u subs go, a very simple one, and maybe you can just think through it, in reverse. So, well, cosine, right? That would have come from sine, so it'd have to be sine 12x. But if I took the derivative of sine 12x, I would then have to multiply by 12. So I need to multiply by a 1/6 here in order to end up with the 2. All right, and then over here we've got the 1/8. Hey, I've got a 1 again, so x. And antiderivative there, well, that would have come from sine as well, sine 24x. But I would then need to multiply by a 24 when taking a derivative. So I need the 1 over 24 there so that it cancels. And this is it, just a matter of cleaning up the answer a little bit. And so here's the final. I went ahead, distributed the 1/4, distributed the 1/8. I went ahead and combined those x terms. You'll get 3/8 x. And then the rest is right there, right? Minus 1 over 24 sine 12x plus 1 over 192 sine 24x plus c, and we got it. Okay, I think that's enough for one video. A couple more examples to come.